Okay, in this section, we will give a brief introduction to self-supervised pre-training, which is a key component in current approaches to solve NLP problems. Okay, so the main goal of pre-training is to learn a good representation. So what makes a good representation? We consider representation good if it contains good features for downstream tasks. So if we have good features, we don't need a complex model to make good predictions. Now, take sentiment classification as an example. Here, the task is to take a sentence such as, the food is good but doesn't worsen our weight, and predict whether the sentence is negative or positive. First, let's consider a very simple feature vector, which is a bag of words feature. In this case, we just take all the words that occur in a sentence and put them into a vector format as the input. So the only information that the model has is which word occurred in this sentence. Now, obviously, then we would need a very complex model to take into account of the interaction between different words. For example, even though we have say positive words such as good, there is a but after that and mention some negative parts. So we do need a complex model to consider different interactions of different constituents in the sentence. Now let's consider a better representation, which actually contains some high-level semantic meaning of the sentence. For example, the topic here is food. The sentiment related to food is negative, and it also talks about service, etc. Now, given this representation, we could easily use a linear model to make a good prediction. In fact, the model just needs to take a look at its sentiment feature. And here is some interesting results from a paper that shows that through unsupervised learning, the model, there's actually some sentiment neuron or sentiment feature emerged in the model parameters. So here we can see that the positive review and the negative reviews can be separated by the output of a certain neuron. So this shows that having good representation is really effective for downstream tasks. Okay, so what else can we do with a good representation? The first advantage is that it enables low resource learning, meaning that for downstream tasks, if we have a good representation, we don't need to learn from large data because we only need a simple model and we can learn that easily from a small amount of data. And second is transfer learning, which means that we have a single representation which can be used for many different tasks. In addition to sentiment classification, if we have a good sentence representation, we could also do question answering or any other language understanding tasks. And finally, metric learning. Sometimes we would like to have a measure of similarity between two pieces of text. Now, given good representation, we also get a similarity metric for free. And all of this enables the model to learn more like how humans learn, which doesn't require large amounts of data and can easily transfer to many other tasks. Now, how do we learn the representation? For any learned neural network, it already gives us a data representation or an embedding. But in most cases, it is task specific. For example, if we learn the sentiment task, then our representation will only contain sentiment related information. But here, by a good representation, what we want is something that can be used for many different tasks. So here, instead of learning on a specific task, we use unsupervised learning to learn from large-scale data. In unsupervised learning, we don't have any labels to form our prediction task. So instead, the key idea here is to predict parts of the input from the other parts. Let's consider the language modeling task. One way to formulate the prediction problem is to predict the future from the past or left to right language modeling. So here we have a prefix, time files like, and blank, and we want to predict the next word. The other type of language modeling is masked language modeling, where we hide one word in a sentence and predict that word from the neighboring words. Both can be used for pre-training. For example, GPT is a model that's using left-to-right language modeling, and BERT uses masked language modeling. Here is an overview of the transformer architecture used by the BERT model, which is a widely used pre-trained model in NLP nowadays. It's essentially a large-scale transformer model. As you can see here, we have position, encode embeddings, and the token embeddings. In addition, we also have segment embeddings corresponding to special markers that segment different sentences. The pre-trained objective is masked language modeling, which we covered just now, and next sentence prediction, where the input are two sentences and output is whether they're consecutive sentences. In addition to BERT, there are many other large-scale transformer models learned by language modeling, for example, GPT-2, Roberta, Albert, etc. So these forms the set of pre-trained models that are most widely used for NLP. Okay, finally, let's look at this pre-train, the fine-tune paradigm. So we have just seen what pre-training does. So after pre-training, we get the transformer model with learned weights. Now, how do we use that for downstream tasks? For downstream tasks, we would use the same model architecture, but the weights are initialized from the pre-trained model, meaning that we copy the weights over to the model that we're going to train on the downstream task. Now, one difference is that during pre-training, the output layer does language modeling, but here the output layer would predict specific labels for the task. So the output layer is initialized randomly and fine-tuned from scratch. This pre-training and fine-tuning approach with large-scale pre-trained transformer models has significantly improved the performance on language understanding benchmarks in the last 2 years.